So what I would like to talk about today is science, technology, engineering, and mathematics in the petroleum industry. And raise your hands here if you are a teacher in the science, technology, engineering, or mathematics field. That's great. Now, if you think you are not, I claim otherwise. I think there's a place for mathematics and science almost everywhere. So I think you're all STEM teachers. And what we're going to talk about today is a part of the petroleum industry called formation evaluation and formation testing. And before I get started with that, I want to sort of ground us in a story. So the story I want to tell you about is about Henry Ford. I think everybody here knows Henry Ford, a giant of American auto industry. And Henry Ford had a problem one day in one of his factories. And the problem he had was he had a generator. And this generator was spinning, but it wasn't producing enough electricity. And all of his engineers couldn't really figure out the problem. So he called the company that manufactured the generator, and they sent over a wise old engineer named Charles P. Steinmetz. Charles Proteus Steinmetz, that was his middle name. And Charles Steinmetz, when met with Henry Ford, refused all offers of engineering help, of advanced instruments. All he asked for was a pencil, a notebook, and a cot. And Charles Steinmetz spent 2 days with this generator, intimately, sitting on the cot, listening to it, watching it run, taking notes, sleeping on the cot, laying down and taking notes. And after 2 days, he climbed up the ladder, he took out a piece of white chalk, and he made an X on one of the panels of the generator. And he instructed Ford's engineers to remove the panel and remove 16 windings from the field coil. And they did that, and it started working perfectly. And Henry Ford was thrilled until he got the bill. So the bill was $10,000. And at that time, that was a king's ransom. And Henry Ford, who was very organized and cost-conscious, said, I really need an itemized bill to understand where this $10,000 came from. So Charles Steinmetz sent him back promptly an itemized bill. And here's what it looked like. It's $1 for making the chalk mark on the generator, and $9,999 for knowing where to put it. Ford paid the bill. So the reason I'm telling you this story is because you're going to realize, hopefully about halfway through this presentation, that formation evaluation and testing is all about knowing where to put the chalk mark. So this is the agenda for today. For those of you who don't enjoy history lectures, I apologize. I'm going to try to make this as fun as possible. I want to talk about early petroleum history to get us all on the same page. I want to talk about the fundamentals of how oil is produced so you understand the kind of questions we want to answer with formation evaluation and testing. And then I want to show the basic oil field technologies that laid the backdrop for the advent of formation evaluation and testing. And the way I'm going to do this is a walk through time. So this is a map of where we are right now. You are here, right here, in 2017. And we're going to go back, way back. I teach PowerPoint too. So we're going to go back over 150 years. And 150 years ago, we lived in a world that was lit entirely by fire. There were no incandescent light bulbs. If you wanted to read at night, if you wanted to do work at night, you had a few choices for your method of illumination beyond just candles and torches. And some of the most fundamental ones were lamps that were powered by either lard oil or whale oil or a material called camphene. Camphene was a mixture of camphor, pine tar, and alcohol. And somewhere in the middle of the 19th century, a man named Abraham Gessner invented kerosene. Kerosene is an illuminant that was distilled from coal. And he named it kerosene after the Greek word kerosalion, meaning wax oil. And eventually he figured out a way to get it out of petroleum, which was much more cost effective. And the killer app for kerosene, which was invented almost simultaneously in the United States and Poland, was the kerosene lamp, very soon after. Well, now we've got a new illuminant and an application to light up your night. And what followed soon after was people trying to figure out ways to find petroleum. And the way that you typically found petroleum in the past was there would be a place in the world, whether it was Romania or Azerbaijan or Pennsylvania, where oil just seeped out of the ground and you would bring a small bucket and collect it and then go sell that oil to somebody who could refine it. That's the way that we collected oil. Well, in 1859, a man named Colonel Edwin Drake, and the truth was he wasn't really a colonel. He found out that when he tried to get investors, it made more sense to put an impressive sounding title in front of his name. And so when he was Edwin Drake, nobody invested, but when he was Colonel Edwin Drake, people gave him money. So he took some investor money and he went to Pennsylvania, Titusville, Pennsylvania, and he endeavored to drill the first well expressly for the purpose of extracting oil out of the ground. This had never been done before. And here's a picture of him, and what you see is him on the right in the top hat, and then to the left is a man named William Smith, who people call Uncle Billy, who enjoyed whiskey, and as did many people in Titusville, Pennsylvania. And they worked on a well using a technology of the time called cable tool drilling. This is a technology still used today to make water wells. And the way this works is you take a big weight with teeth on bottom of it, you pull it up with a cable, and you drop it. And you repeat over and over and over again. That's how you would make a well. And what they noticed was the well they were making was so deep that the ground started caving in after it. So they also invented something else called a casing. And a casing is nothing more than a metal pipe run down that well to keep the walls from caving in. And when they got finished with the well, it was 69 feet deep, and it produced an amazing amount of oil for the time. So the people who were used to collecting oil in buckets now had so much oil coming out they didn't know where to store it. As I mentioned, the people in Titusville enjoyed their whiskey, and the one thing they had plenty of was empty whiskey barrels. So the 40-gallon whiskey barrel, they brought 20 of them a day over and filled them with oil. Filled them. As a matter of fact, that unit of measure has persisted to this day in America. The barrel of oil is based on the size of the whiskey barrels used in Titusville, Pennsylvania. They were 40 gallons. We use 42 gallons now. It's not too far off. So that's where it came from. And to put this in perspective, compared to whale oil, in a week, this well could produce more oil than a 4-year whaling voyage. So that leads us to the next slide. A couple of points of economics. We're going to take a snapshot of the 1850s. One snapshot is the price of illuminants and their quality. Another one is whale oil production versus the Drake well. And a couple of things you can see here from the whale oil graph is that the Drake well had been drilled at a point when whale production had been going down. So less whales were out there, and whale oil was getting more expensive. The other thing to look at was the price and the quality of all these different illuminants. So if you looked at this table on the left, and you had a choice for a gallon of illuminant to buy, which one would you choose? Camphene, right? It's got good quality, and it's got a reasonable price. Well, in 1861, just a couple years after the Drake well, something interesting happened in America. Does anybody know what happened in 1861? Civil War. I love being in a room full of educators. That answer never comes across when I'm at work. Yes. So the American Civil War started in 1861. And believe it or not, there was a time in American history when there was no income tax. Isn't that cool? But they needed to raise money for a federal army. And the way that you raised money at that time was you taxed goods and services. And one of the goods that was taxed was alcohol. People drank a lot of alcohol. They decided to tax it. And they taxed that alcohol at $2 a gallon. Now, that tax on alcohol, through a interesting snafu of bureaucracy, was extended to anything that contained alcohol, including camphene. Camphene overnight rose to $2.50 a gallon based on this $2 tax. So now, which of these illuminants would you choose?
Well, wouldn't they all have raised $2?
They don't all contain alcohol. Only camphene contain alcohol. I picked kerosene, right? And the oil industry took off. So there's 3 perspectives I want to talk about from this information. The first perspective is if you believe in interventionist policies, then this tax on camphene was an effective subsidy for the petroleum industry and made people want to invest in petroleum even more. The free market point of view is that, well, whale oil had peaked, it was getting more scarce, natural market forces would have made oil more attractive in a very short time anyway. I have a third perspective. My perspective is when you look at that graph of whale oil and you see how much they were in decline, it's clear that the oil industry saved the whales. Right? So actually, we have a lot in common with Greenpeace. Sometimes it seems like we fight. Truth is that we have the same idea in common. So when we started refining oil for kerosene, there was an interesting byproduct. There was this sort of clear yellowish liquid, and it was volatile, it was dangerous, explosive, and they call it gasoline, and they typically just threw it away. They had no use for it until a little bit later. So what's the killer app for gasoline? The motorized automobile. And in Europe, again, almost simultaneously, like the kerosene lamp, two gentlemen invented the automobile at the same time. One was Carl Benz, one was Gottlieb Daimler. And this was in 1886. Fun story about Carl Benz is that even though he invented a motorized vehicle, it was his wife who was the test pilot. So Bertha Benz, and she wasn't the test pilot because he asked. She was the test pilot because she saw this vehicle sitting on the property and said, that looks like fun. I'm going to pack all the kids in it and drive to go see the family next door. She drove 106 kilometers in an untested, invented vehicle. And on the road, she made an invention with the help of a tailor on the road. She invented brake linings because the car wouldn't stop. So Bertha Benz invented the modern brake lining. Interesting story about Gottlieb Daimler is that in 1900, he received a massive contract to make 36 automobiles for sale in Europe with a financier named Emil Jelinek. Everybody here knows the name Emil Jelinek. You don't know who Emil Jelinek is, but you know his daughter. So on the condition, the condition that Emil Jelinek made was, I'll pay for those cars and I'll give you the order if you name your next engine design after my daughter Mercedes. And that's where the name Mercedes was born. So that sets the backdrop for another event that happened in the oil industry called the Spindletop Well. So now you've got automobiles in production, and people in Texas decided to drill very, very deep for oil. A place near Beaumont called Spindletop. That's the star on the map over here. And they drilled with a technology called a fishtail bit. If you look at a fishtail bit, it looks almost exactly like a big version of the bit you would use to drill through wood. It's meant to drill through wood. And they used it to drill through rock fairly inefficiently, but they got over 1,000 feet deep. And when they hit this depth of 1,139 feet, something remarkable happened. Oil started spewing out of the ground at an unbelievable rate. For the first 9 days of production, this well produced 100,000 barrels per day. And then the question is, well, is that a lot? Well, here's the perspective on it. That amount of oil overnight became 58% of American oil production. One well. 1 year later in that field, the first 6 wells drilled had more oil production than the entire planet Earth combined. The Texas oil boom was on. So that leads the vision in your mind that, well, the way you drill an oil well is you drill a hole in the ground, and there must be a gigantic gas tank of oil under the ground somewhere. I make that hole, the oil comes out, and then I dance all the way to the bank. So here's where I want to get on the same page about, wow, how oil is produced. This is not actually what happens. So what the underground world actually looks like is solid rock. Layers and layers of solid rock. But these rocks are different types of rock, and they have different characteristics and different fluids inside of them. And over time, formations of rock might contain a layered combination of water at the bottom, oil at the next level, and gas on top. And they would continue to rise out of the ground unless they encounter another kind of rock called a cap rock. A cap rock is an impermeable layer of rock that basically traps this oil and gas in one place. And this is what we refer to as the formation. So later on when I talk about formation, this is what I mean. And the reason why they do this is because the densities of these fluids are different, and they are immiscible, so they don't mix together very well. So you're going to have these layers of fluid. So if you were to drill a hole through that formation in the ground, through all of those layers of rock, water would come out of the water-bearing rock, oil would come out of the oil-bearing rock, and gas would come out of the gas-bearing rock. And they would all come to the surface in a mixture. So if you were interested in making a water well, would this be good? If you're interested in making an oil well, would this be good? Why? Yeah, how do you unmix it? It's really expensive to unmix all that stuff, if anybody's ever tried to do it at home. So I'm going to talk about some technologies that were formed to solve some of these problems. So the first fundamental technology is the modern rock drilling bit. This was a 2-cone bit invented in 1909 by Howard Hughes Sr., not Howard Hughes Jr., who was played by Leonardo DiCaprio in The Aviator. This was his father. So Howard Hughes Jr. actually, a decade or two later, made an important innovation. He added a cone. He made a 3-cone bit. So that was Howard Hughes Jr.'s claim to fame. This bit could drill through rock 4 times faster than a fishtail bit. And as a matter of fact, we still use these kind of bits today. The second major innovation is to solve the problem of all those fluids coming out in an unorganized way. A man named Earl P. Halliburton, who lived in Duncan, Oklahoma, invented a method of putting a metal casing in the well and then injecting cement into the annulus between the metal casing and the rock. So now no fluid would come out of the well. Well, you don't really want no fluid to come out of your well. You want the right fluid to come out of your well. So the last innovation was invented by a man named Sidney Mims. And late one night in Los Angeles at a diner, Sidney Mims sold his patent to two men named Lane and Wells. And this patent was something called the perforating gun. The perforating gun is essentially a serial machine gun that has bullets all along its length. And wherever you want to make holes in that casing to start producing fluid, you fire the bullets. And it makes holes through the casing, through the concrete, into the rock, and now fluid is free to come out at a place of your choosing. So let's put all these together. I use my Hughes bit to drill a hole in the ground. I now have an open hole in the ground. I case that hole, and I cement it, so now nothing is coming out of the well. And then at the place where there is oil, I perforate, and now only oil is coming out of the ground into my well. So what's missing from this situation? Where to put the holes. Where to put the chalk mark. And that's where formation evaluation comes in. So now we're going to go across the Atlantic to France. And we're going to talk about two brothers named Conrad and Marcel Schlumberger. And Conrad and Marcel Schlumberger had this idea. They said, why don't we use the fact that oil has a very high electrical resistance and the water underground has very low electrical resistance, and take measurements of a well and see where the oil is and where the water is. And to illustrate this, what I'm going to show you is this is a resistivity cell. It's got two electrodes on it, the same material, copper. And I'm going to measure the resistance through this salt water in this jar. It's right here so you can see it. You see some numbers there? That's a finite resistance. It actually is conducting electricity through that salt water. Now, I'm going to take the same system and ask it to conduct electricity through oil. And what you see is a reading that basically says, I've given up. This resistivity meter cannot measure that level of resistance. It's almost infinitely resistive. So what the Schlumberger brothers did, they made a tool that would go into the well, and it had 4 electrodes on it. And 2 of the electrodes were dedicated to measuring the resistivity of the rock and the fluid inside the rock at depths in the well. And what you see here is their first hand-drawn log. And this, I'm going to lay some blue lines on it to make it more visible to you, because their handwriting is a little bit difficult to see. But what you see here is the vertical axis is resistivity, as measured by their tool. The horizontal axis is depth, getting deeper in the right direction. So, when you look at this, knowing that resistivity is going up in the vertical direction, where is the oil? Right there? That's right. And now people could drill an experimental well and know at what depth the oil would be. They knew where to put the holes in the casing. And this technology took off. This is the beginning of formation evaluation. So, to cap off this period of history, one last observation. So a couple decades went by, and a 7-year study was launched by the American Association of Petroleum Geologists. And what they wanted to study was, if you drilled a hole in America, what were your chances of actually making money off of it? What were your chances of oil coming out of the ground? And they conducted a study, and one thing they found was some states had oil and some states didn't. It's an unfortunate matter of geological history. But they also collected a painstaking level of data about every single well drilled in the United States over a 7-year period and whether it produced or did not produce oil. And I can sum it up in this graph right here over a 7-year period. What you see here is your chances of getting oil out of the ground every year, depending on whether you picked one of 2 methods for locating your well. The first method is something called a non-technical basis. Now, a non-technical basis is a nice way of saying a guess or a rumor, like my Uncle Billy said, I think there's oil here, Or this looks like an oily place. That's a non-technical basis. A technical basis would be using any of the emerging technologies at the time to figure out the right place to drill for oil. And what you can see here is, if you used a technical basis to drill a hole in the ground, your chances of getting oil out of the ground were way higher than any other method. So now you have a technology in place, and now people have realized how valuable it is. Now it's an industry. Okay, so to sum all this up, this is my summary from my history class. I hope it was entertaining. First thing is, there's an escalating demand for petroleum. Started with illuminants, then it became useful for lubricants, and then for automobiles and internal combustion engines, and eventually world powers would realize how useful petroleum was in powering weapons of war. Churchill famously switched the naval fleet of Britain from coal to oil in a choice that affected history for a long time. We also have the advent of different drilling and production technologies to help you get to the oil and get it out of the ground. And also the advent of technologies to tell you where the oil was once you drilled that hole. And pretty convincing proof that there was a value for having this information. So now let's look at not only then but today. The questions that we want to answer with formation, evaluation, and testing were the same back then as they are today. The first question is, where's the oil and gas? And one element is, what latitude and longitude should I be drilling? And at what depth is the oil and gas going to be? Then there are a couple more questions that you want to answer. One is, how much is down there? Is it worth drilling a hole in the ground if the reservoir is this teeny? Now, suppose it's a very large reservoir. There's still another question to answer, which is, even if the reservoir is large, how easy or difficult is it going to be to get the oil out of the ground? So what I'm going to show you next is some of the science and math behind how to answer those questions. So the first question, how much is down there? So the science that goes into figuring out how much is down there is dependent on a few key parameters. Two of the most important parameters are the area of a reservoir and how thick it is. Most reservoirs are characterized as being very large areas, like acres in size, hundreds of acres. And their thickness is characterized in feet, maybe tens of feet. So if you know that size, and if it were all filled with oil, you'd be at the end of your equation. You'd know exactly how much oil was down there, but that's not the way it works. The other thing that impacts how much oil is down there is porosity. How much room is left in the rock for fluid? And even beyond that, most rock is complicated. It's not just filled with oil or just filled with water. It's filled with a combination of them. So based on a resistivity measurement, you can tell how much of the fluid inside the rock is oil and how much is water. And I want to illustrate this concept of porosity. So what I have here, you see up on the slide, and hopefully you'll see on the camera as well, is a couple of porosity cells that I've made here. I've got porosity cell A, and I've got porosity cell B. And the biggest difference between these two cells, they have the exact same starting volume. If there were no rocks inside of them, no water, they'd have a volume of almost exactly 32 ounces, 1 quart. But I filled A with large rocks, and I filled B with large rocks and then small rocks. So the question is, how much room is there for water inside A, inside B? Which one has room for more water, A or B? A? Well, I think it's A too, and we're going to find out through an experiment. So I'm going to pour all the water out of A. Glad I got the big cup. And then I'm going to pour all the water out of B. I'm so glad that worked. Nothing quite like experimental science. So you're right. A has more fluid, more room for fluid. It has a higher porosity. A has a porosity of about 40%, and B has a porosity of about 23%. And I'll tell you, I'm so glad this worked because at my home, the first time I did this, these came out very close to each other, and I'll tell you all about that story after the talk if you want. It was very embarrassing. I was having a moment. So now we're going to combine all this information into one equation that tells us how much original oil is in place in our reservoir. This is the equation for original oil in place. and we're going to start building this equation one step at a time. So the first part of the equation is, if I know that I have a reservoir of a certain height in a certain area, if I multiply those two things by each other, I get a volume. And if it was all oil, I'm at the end of the story. But I then have to multiply it by the fractional porosity, for example, 20%, to know how much of that area is consumed by rock and how much is available for fluid. And then finally, if I know how much of that fluid fractionally is made of water and not oil, that's SW, I multiply by this factor to know how much oil is remaining in those pores. And that's the equation. And we add a couple coefficients here. One is to convert acre feet to barrels, and one is a way of converting from the size of an oil barrel in the underground environment to a surface environment. But that's the equation right there. This is how we know how much oil we have underground. So the next question that we have is, how difficult is it going to be to retrieve? So I could have a gigantic reservoir down there, but if I can't get it out of the ground, it's not very useful to me. So the three factors that play into this are pressure. So over millions of years, this gas, oil, and water reservoir have been increasing in pressure through chemistry and pressure and temperature. And it's almost like, I hate to say this on film, it's a keg. It's like a keg. If you pump on a keg, you're pumping up the gas cap on top of a keg, and the beer comes out. Well, the oil does the exact same thing, kind of like the Lucas gusher. But if you don't have a lot of pressure, it's not going to come out very easily. What also influences the fluid coming out is how difficult the geology makes it to flow out. Permeability is a property of rock. It's related to porosity, but it's not the same as porosity. So if you can imagine a piece of Swiss cheese that had a lot of holes in it, but if none of the holes were connected, it would have a high porosity, but almost no permeability. So there needs to be a path between holes in the rock for the fluid to get out. And finally, the fluid itself offers some resistance to flow. So fluid has a property called viscosity, and things that are more viscous don't flow as easily. And so I want to demonstrate viscosity as well. Another experiment here. So what I've got is a jar full of vegetable oil, and we measure viscosity in a unit called centipoise. 1 centipoise is about the viscosity of water. So oil, this vegetable oil, is about 80 times the viscosity of water. So what I'm going to do is I'm going to pour this oil in a container. I want you just to sort of mentally remember how long it takes to pour it out. Longer than the water, right? But not tremendously long. You have nowhere to go today, right? All right, that took us some time. Now what I have is a jar full of honey. So honey is 2,000 times the viscosity of water. I would have used ketchup, but we'd be waiting for a much longer time. So now I'm going to pour out this honey. So I'm just going to leave that there. And we're going to see if any honey comes out over the course of this lecture. So that's a lot of viscosity. Now, if you think that's a lot of viscosity, I want to introduce you to the second longest running experiment on the planet. This experiment has been conducted at the University, the Trinity College in Dublin, since 1944. And this experiment consists of putting tar in a funnel and waiting for it to drip through the funnel to measure the viscosity of tar. They usually get a drop about once every 10 to 15 years. So this is slow science. And I'm going to play a video of this for you. Don't worry, I sped it up. So what you're going to see is about 2 seconds per day in the last time before the most recent drop was filmed. It's exciting. Come on, drop. Come on, days are going by. It dropped. Whew. Say what you will about cricket and baseball, but this to me is excitement. So based on these experiments, they've measured the viscosity of tar as 20 billion times the viscosity of water. And this figure differs a little bit between the University of Dublin and the University of Queensland in Australia, where the world's longest running experiment occurred. I suppose you're wondering why I didn't show you the film of that. It's a little bit of a sad story. So around the 1980s, the University of Queensland, running an experiment since 1927, same looking experiment, a man named John Mainstone decided, we're going to put a camera on this. Nobody's ever around to see a drop fall. We're going to film this finally. And they did so. And in 2000, some scientists woke up in the morning and found a drop had fallen. They were so excited. They ran over to the camera and found out that they had not turned it on. So, University of Dublin put more than one person in charge of making sure the camera was on. So even though University of Dublin is the second longest running experiment in the world, they're the first one to get camera footage of a drop. University of Queensland, Australia in 2014 finally filmed their first drop. But sadly, John Mainstone had passed away a year earlier. I know, it's sad. The really sad part is to find out this is actually the third longest running experiment. At a university in Wales, somebody dug up in a cabinet another one of these that had been sitting there since 1917. So now this is the third longest running experiment in the world. So let's put all this together to figure out how much flow, or how easy it is to flow fluid out of the rock in an oil well. So the equation for flow through rock was developed by a guy named Henri Darcy. He was using it to describe the way fountains fed water to them in Dijon, France, back in the mid-19th century. And this is called Darcy's law. And what Darcy invented was the concept of permeability. We call it K. And the more permeable a rock is, the easier fluid flows out of it. And we measure permeability in a unit called Darcy's, named after Henri Darcy. Now, the more pressure that's driving your fluid out of the ground also increases your flow. That makes sense. More pressure, more flow. That's why it's in the numerator. But viscosity, the more viscosity you have, the more it impedes your flow. And that's why that quantity is in the denominator. And there's two more terms that are geometric. One is area and one is length. So if you produce out of a large hole in the rock, you're going to produce more fluid. That's why A is in the denominator. If the fluid has to travel a long distance to get to your hole, it's going to impede its flow, and that's why it's in the denominator. This is the equation for flow through porous media. That's how we figure out how difficult it is to get oil out of the ground. So now we have the math. We have the equations. We know what quantities to measure. Let's go get that information. Let's go into an oil well and find those things. So what I want to show you is what things look like at the bottom of an oil well. So that's it. No human senses are going to help you figure this information out in an oil well. It's a dark place. It's underground. It's hard to communicate. There's nothing there. And to make life even worse, the downhole environment has some very serious challenges associated with it. So whatever sensor system I lower into that well, it has to overcome the following problems. One is pressure. The pressure inside of an oil well is gigantic. It can be anywhere from 5,000 to 35,000 psi. So my point of perspective on this is the deepest point in the ocean, Mariana Trench, is only 16,000 psi of pressure. So the highest pressure in an oil well is twice that pressure. Very challenging environment. Temperature. The highest temperatures you can see in an oil well can be anywhere from 350 to 500 degrees Fahrenheit. That's somewhere between cooking a chicken and a pizza. So imagine making your iPhone work in an oven. It's very difficult. And if that weren't bad enough, the fluids inside of an oil well can be very, very aggressive. They can be corrosive. You can have salt water almost all the time. Salt water corrodes metals. There's a substance called H2S, which is about the scariest gas on the planet. It's lethally toxic, it's corrosive, and it's flammable. Basically the scariest thing you can imagine. And also at certain temperatures and pressures, carbon dioxide can be corrosive. And to cap the whole thing off, our geometric limitations in a well, nobody wants to drill a well 3 feet in diameter. They want to make a well as small as possible because it costs less. We have to fit these instruments into a diameter of hole that can be anywhere between 6 and 12.25 inches in diameter. So these are some pretty serious engineering challenges. And the technologies that we have to bring down there are split into two families: formation evaluation and formation testing. And what I want to talk about here is the difference between those two families. It's not entirely an arbitrary difference. Formation evaluation tools tend to be physics intensive. They use electromagnetic or nuclear or acoustic properties to bring back information. So, for example, an acoustic or a seismic tool creates sound waves and listens to the way they bounce back to understand the boundaries in the rock of the geology. Gamma ray tools operate very much like an X-ray at the hospital. They tell you something about the density of the rock. If it's difficult for a gamma ray to get through a rock, it means it's more dense. Electromagnetic operations are very much like the Schlumberger brothers, using the resistivity of the fluid in the rock to bring back information about the basic fluid type. The one technology on here that doesn't have a very good analogy is neutron technology. We don't use this in medicine. And I'm going to explain that in one slide afterwards because it's kind of special. We use it to measure porosity. And NMR technology, most people know this more familiarly as MRI, magnetic resonance imaging tools. What this does for the human body, we can apply downhole. We can bring back information about the materials, a 3D map of the underground environment, and also how mobile the fluid is, how much it can move. And these measurements are most useful for sizing a reservoir, knowing how dense it is, how porous it is, and getting a basic idea of the fluid types, gas, oil, or water. And they're non-invasive, which means they're really analogous to things like echocardiograms or x-rays. You don't have to remove material from the patient in order to learn about what's going on here. Formation testing tools are mechanics intensive. So these tools use high power electric supplies to drive motors or solenoids that in turn might drive pumps, to drive hydraulic systems, to make mechanical systems do things like pull fluid out of the rock or pull a rock sample out of the rock. So they are invasive. They are invasive. These things are most useful for figuring out the pressure in the rock, the mobility of the fluid in the rock, which is due to both viscosity and permeability, and for detailed fluid chemistry. So if you want to get more information than just is it oil, is it water, is it gas, this is most useful because we can take a sample into the tool and bring it to the surface for analysis. And this is more analogous to taking a blood sample or a biopsy. So to couch these in medical terms, that's kind of the split between formation, evaluation, and testing. So what I want to show you next is one example of a formation evaluation tool and one example of a formation testing tool in detail. So the example I want to use for formation evaluation is a neutron porosity tool because this is the one that most people don't have a frame of reference for. And I love nuclear technology too, so I want to talk about it. So the way a neutron porosity tool works is this tool has a neutron generator somewhere in its body. And somewhere else in the tool, it has a neutron detector. And when this neutron generator is turned on, it screams neutrons. And those neutrons fly into the rock of the geology. And when they do, one of a couple things will happen. Neutrons don't care about electrons. They only interact with nuclei. And if they encounter a large nucleus, like a silicon or an oxygen nucleus, it's a little bit like a ping pong ball hitting a bowling ball. The ping pong ball bounces right off, it doesn't lose much energy, and the bowling ball is hardly disturbed. So the neutron has very little energy loss. Whatever speed it was traveling at, it continues traveling at that speed. But when a neutron encounters a nucleus about its same mass, like a hydrogen nucleus, a proton, it behaves very much like a billiard ball. It hits that proton, and it gives away about half of its energy. So if it hits hydrogen, it's going to slow down. So what's interesting about the pores in the rock is that regardless of whether those pores are filled with gas or oil or water, water is composed of hydrogen and oxygen. Oil is composed of carbon and hydrogen. What do those two things have in common? Hydrogen. So it doesn't matter what the pores are filled with, they have a lot of hydrogen atoms. So these neutrons, if they travel through this rock and they encounter almost no hydrogen atoms, they'll get back to that sensor in large populations. However, if they encounter lots of hydrogen atoms, they're going to slow down, and sometimes they slow down so much they don't even make it to the detector at all. So in the end, hydrogen slows down neutrons. Porous rocks are full of hydrogen-rich fluids. More pores means less of these neutrons make it to the detector. So less neutrons detected means higher porosity. And this is how we measure porosity. Cool, huh? So now I want to talk about a formation testing tool, a pressure and sampling tool. These tools are more invasive. When these tools are used, they set themselves up against the rock wall. And when they do that, they engage a rubber donut. It's actually almost the size of a glazed donut. And it's called a packer. And this packer's job is to make a seal up against the rock. And when it does that, the fluid inside the rock is now in communication with a cavity inside the tool. And in that cavity, I have a drawdown piston That piston is very much like a syringe. And I also have a pressure sensor inside that cavity. Now, when I first turn on this pressure sensor, before I even set the tool against the wall, the pressure that I measure in that sensor is the pressure in the borehole right here, because that's the fluid that was inside the tool. Now, if I draw back that drawdown piston like a syringe, what do you think happens to pressure? It goes down. I'm increasing the volume, and it's very difficult for the fluid to come out of the rock. So if you've ever seen a child trying to suck on a McDonald's shake through a straw, and they suck so hard that their eyes start to cave in, this is what's happening inside the tool. The pressure is going down. But then something else happens. The rock allows fluid to flow into the tool through that hole in the packer. And when the fluid flows through the rock into the tool, the pressure rebounds. And when the pressure rebounds, it builds up at a certain rate. And that rate tells you something about how mobile the fluid is based on its permeability and its viscosity. And the pressure, the equilibrium pressure that is reached right here, why is it lower than the pressure originally? Fluid has stopped flowing out of the rock. And the reason why the fluid has stopped flowing out of the rock is because the pressure in the rock is the same as the pressure at the sensor. So now this pressure measurement tells me the pressure of the fluid in the rock at that depth. Now I'm going to show you a different curve. See this red one? It's a different curve. So compared to the blue curve, what do you think the mobility of the fluid is? Red versus blue. It's more viscous. Maybe it's less permeable, right? It has lower mobility. This is going to be more difficult to get the fluid out of the rock at this depth. But the pressure, it's the same. So even though the pressure is the same, this is a location where life is going to be harder for you to get oil out of the rock. Now, in addition to these properties, once I have this fluid inside the tool, I can then bring it to the surface to do very detailed lab analysis on it. So if I want to know exactly what kind of oil and gas or water I have down there, I can do that at the surface. We even have tools now that can do these measurements in situ, in the tool's downhole. So to close up the whole talk, what we've looked at is answers to what we want to know. We want to know where the oil is. We want to know how much is down there and how difficult it's going to be to retrieve. And when you get a chance to walk the floor today, I want you to keep your eyes open for tools that do just this, and tools that do more advanced work as well, like telling you what quality of oil or gas it is. How easy is it going to be to transport, process, and refine? And how do I manage these reservoirs most effectively? And in the end, the reason why we're all here in this room is because we are STEM people. What you saw today was the science of the physical phenomena that describe the geology. You saw the technology that was invented in order to bring new drilling techniques, new production techniques, and new information gathering techniques to the oil industry. And the engineering that was needed to overcome the challenges of such a difficult environment, to package those technologies and industrialize them for real use, and the mathematics that brings us the answers to the questions that we have. This is who you are. This is who I am, STEM. And I have a lot of people to thank for the material in this presentation. I hope you enjoyed it. And that's all I have. Thank you.